Okay, I'm gonna share the slides. Go to presentation mode. Okay, can you all see it fine? Okay, good. So my name is Kaivan Kamali. I work at the Galaxy Lab at Penn State at Anton Lab. This talk is about singular value decomposition, a machine learning technique that has applications in many different areas. Single value decomposition calculations are very math heavy. I've tried to simplify it with examples. So we discuss concepts rather than formulas. Hopefully it'll be clear. So this is the outline of the talk, linear algebra basics, then transformation matrices, what are eigenvectors and eigenvalues, eigen decomposition technique for symmetric matrices, what are singular values, and singular value decomposition technique for non-symmetric matrices. Finally, I'm going to talk about applications of SVD and how to add SVD in Galaxy. So matrices, which is the plural of a matrix, is just a rectangular or square array of numbers arranged in rows and columns. So a matrix size is determined by the number of rows and the number of columns. So in this matrix A that displayed here, there are 3 rows and 2 columns, so it's of size 3 by 2. There are different types of special matrices. The square matrices have the same number of rows as columns. This is a 2 by 2 square matrix. Row vector, there's only 1 row, multiple columns. Column vector, 1 column, multiple rows. And standard way to represent a vector is a column vector. Diagonal matrices have only elements on the diagonal, everything else is 0. Matrix operations, addition, you just add the corresponding entries in the 2 matrices that you're adding. So if you add these 2 matrices, you add, for example, 1 and 5, that will give you the value 6 and so on. Scalar multiplication is you add a scalar, something that's not a vector, by a matrix. It's very simple. You just multiply corresponding entries by that scalar and you're done. Transposition, it's an operation in which you replace the rows with columns. So if you have A with row 1, 1, 2, row 2, 3, 4, you just put row number 1 in column number 1, row number 2 in column number 2, and that's the transpose of a matrix. So if some matrix is equal to its transpose, that matrix is called symmetric. So if you transpose it, you still have the same matrix. There's also matrix multiplication. That's only allowed if you're multiplying A and B, if the number of columns of A matches the number of rows of B. So if A is size m by n and B is size n by p, the result would be m by p. And as you can see, the number of columns of A matches the number of rows of B. And every element in the resulting matrix is calculated by this Cij formula. It looks a little bit scary, but all it is that you take row 1 and column 1, multiply the entries correspondingly, and add them up. And you repeat that for every element in the resultant matrix. There's something called the concept of inverse of a matrix, represented by A minus 1. If you multiply the inverse of a matrix by a matrix, you get an identity matrix. So this is similar to math in a scalar world. When you have a number and you have the inverse of that number and you multiply them together, you get 1. It's the same concept applied to matrices. There's also this thing called the dot product. You have 2 column vectors. The dot product would be you multiply corresponding entries and you add them up. So it's represented with A dot B, and you transpose A multiplied by B or transpose B multiplied by A. So this is commutative. You can swap the order. A vector is something that has a length and a direction. And if you want a vector whose, you can calculate the length of the vector by the formula given right next to length of u. It's basically the square root of dot product of u in itself. And if you want a vector that is normalized, that is the vector that has length of 1, you just divide the vector by its length. So that would be a vector that has the exact same direction, but the length is 1. So we want to work with matrices that have a length of 1, not different lengths. And finally, vector space. It's a set of vectors that can be added or multiplied by scalars. We're going to say that a set of basis of a vector space. That they are a set of vectors that are linearly independent and span the vector space. So let's break these two. Let's just define what each of these two things are. Linearly independent just means that if you have a set of vectors, none of them can be expressed as a linear combination of others. Okay, they're independent. And spanning means all of the vectors in the vector space can be expressed as a linear combination of those basis vectors. So, I mean, for two-dimensional Euclidean space, you know, we have an X and Y direction. The basis vectors are 1, 0 and 0, 1. You know, that's if the number of basis vectors is 2, we say the dimension of that vector space is 2. It could be n-dimensional, as we've shown next. We would have n basis vectors, and any point in an n-dimensional space can be represented by the formula at the bottom. X is a1 v1 all the way to an vn. And if you transform this to a matrix multiplication, it would be a row matrix multiplied by a column matrix. So generally the row matrix, the a1 all the way to an, they are the coordinates of that vector in that relative to that basis. And going back, if you see the basis vectors row vector, that's called a change of coordinate matrix. So you can you can calculate the coordinates in two-dimensional space from the coordinates in some other basis based on multiplying it by the inverse. Okay, so we talked about some of linear algebra basics. Now let's talk about matrix transformations. So any linear transformation can be represented by a matrix. A matrix can also represent nonlinear transformations, but we're not going to discuss that. So any linear transformation is represented by a matrix. So a transformation could map an n-dimensional space to an m-dimensional space. And the way it happens is that we multiply a vector, which is n-dimensional, by a matrix, which is m by n dimensional. And the result is a transformation of that vector. So there are different types of transformations, like, if you will, standard transformations. One of them is called rotation. So you have a matrix X shown in blue. Its coordinates are 1 and 0, and you want to rotate it. The matrix that does the rotation is given by A, cosine of theta, sine of theta, minus sine of theta, cosine of theta. So if you plug in the theta, that is the angle that you want to rotate X, you could multiply A by X and you're going to get AX. In this case, I used 45 degrees. Another transformation is stretching, and stretching could be along any line. Here, I'm stretching along the X axis. So what the matrix A does, it doubles the X value, but doesn't change the Y value. Here, I'm stretching along the Y axis, where the X value remains the same, whereas the Y value is doubled. And here, I'm doing a reflection around the X axis. So the matrix A does the reflection around the X axis. I could also do a reflection around the Y axis. Again, the matrix A gives a reflection around the Y axis. So there's also another transformation called shearing. It's basically, let's say you have a rectangle and you push on top of it, and it turns that rectangle into a parallelogram. But we're not going to discuss it, because the whole idea is that any transformation, any linear transformation, can be represented by 3 transformations in sequence: rotation or reflection, followed by scaling, followed by rotation and reflection. That's the whole idea of single value decomposition. So you have a matrix that represents a transformation. You can represent it by 3 sequential transformations: reflection or rotation, followed by scaling, followed by reflection and rotation. So before we get there, we have to define these concepts, eigenvectors and eigenvalues. So we have a transformation matrix A, and we have all the points that are 1 unit away from the origin. If you plot them, that would be a circle, that any point on it is 1 point away from the origin. So we transform the circle, we're going to get an ellipse on the right-hand side. So I picked 2 points on the original circle, x1 and x2, and I've also shown the transformation of those 2, which is called t1 and t2. So anyone, as we said, a vector has a direction and a magnitude or length. Anyone sees anything special about t1 and t2 relative to x1 and x2? In terms of magnitude or direction?
The angle also got changed.
Correct. So T2, as you can see, not only the magnitude changes, it is bigger than x2, but the direction also changes. But for T1, only the magnitude changed. The direction, it's on the x-axis, it didn't change. So this is if you multiply a matrix by a vector and the direction doesn't change, that vector is an eigenvector of that transformation matrix. So x1 is an eigenvector of a transformation matrix A because the direction did not change, only the magnitude changed. So A does not change the direction of X, only changes its length. If you want to represent this mathematically, you say AX equals lambda X. And X is the eigenvector, lambda is the eigenvalue. How much did that matrix X stretch or compress? That's given by lambda. So this has an important ramification because AX is a matrix multiplication. And as we saw, where is it? As we saw here, we have to calculate this Cij equals sigma for every entry. So it is costly. Matrix multiplication, if you have 1,000 by 1,000 matrix, it's going to be very costly. But the beautiful thing about eigenvectors is matrix multiplication becomes scalar multiplication, which is linear. It's very fast. You can just multiply all the entries by a value and you're done. So now we're going to calculate. I'm not going to discuss how eigenvalues and eigenvectors are calculated because there's already too much math in this presentation. It's actually very simple, and both NumPy and scikit-learn, they have a call that you can calculate the eigenvectors, eigenvalues. But I'm going to talk about the property of eigenvalues and eigenvectors. And we're going to do it, we're going to do 2 examples. One for a symmetric matrix, one for a non-symmetric matrix. So A on the left is a non-symmetric matrix, okay? So I'm going to convert the circle on the left, and I'm displaying both the eigenvectors of A on both graphs, on the circle and the transformed ellipse. As you can see, going from a circle to an ellipse requires stretching the circle in a couple of directions. Like you expand it in one direction and another direction, and maybe you tilt it a little bit, which has happened in this case. These eigenvectors do not tell us anything about the direction of the stretch. They're irrelevant to the direction of the stretch. But if we repeat the same exercise for a symmetric matrix, this is a symmetric matrix A. If you transpose it, you get the same matrix. Here, I have the circle on the left and the ellipse on the right, and I have the eigenvectors superimposed on both of them. As you can see, the transformed ellipse, the direction of the stretch are represented by V1 and V2. They're perpendicular. You know, if you stretch it in those 2 directions, you go from that circle to that ellipse. So that's important property number 1 for symmetric matrices. Property number 2 is every eigenvector comes with a corresponding eigenvalue. That was the multiplier, right, in the first example that we discussed. If you multiply that multiplier by the vector, you get a vector that has the same direction, only a larger scale. If you multiply lambda1 and lambda2 in V1 and V2, you get what you have on the right-hand side. The maximum amount of stretch is given by eigenvector multiplied by eigenvalue in both directions, the red and blue. So that's the important property of eigenvectors and eigenvalue for symmetric matrices. So symmetric matrices, they have to be square. Not all square matrices are symmetric, but any symmetric matrix is square. And if it's n by n, it's going to have n eigenvectors and n real eigenvalues, real as opposed to imaginary square root of -1. We're not going to get there. So eigenvectors have the property of being linearly independent and orthogonal. So you can express any of those vectors in terms of the other one. That's good. They're linearly independent and they're orthogonal. That means they're perpendicular to each other. So a transformation performed by matrix A does stretching and shrinking along its eigenvectors, as we saw in that circle to ellipse transformation. And the amount of stretching and shrinking is proportional to the corresponding eigenvalue, okay? Finally, a symmetric matrix is orthogonally diagonizable. So what that means is, if we have a matrix A, we can express it as V, D, V transpose, where V is the eigenvector matrix, and D is a diagonal matrix with eigenvalues on the diagonal. I'm going to show that right now. This is a technique called eigendecomposition. So if you have a symmetric matrix, you can decompose it. You have replaced A with these three matrices multiplied by each other. And it has some interesting properties. So this is a formula, A equals V, D, V transpose. V is you can think of it as a matrix where every column is an eigenvector. In an n-dimensional space, eigenvector has n values, okay? And then you have a diagonal matrix, sigma, where the eigenvalues are on the diagonal, everything else is 0. And finally, you have the same matrix V transposed at the end. So you multiply sigma by the transpose matrix, you get the thing on the right. And the one assumption is that the sigmas are in descending order. So sigma 1 is bigger than sigma 2 and all the way to sigma n. And if you do the multiplication again, you would get A equals 2 on the fourth line, lambda 1, V1, V1 transpose, all the way to lambda n, Vn, Vn transpose. So what does this mean? This means that we have an n by n matrix A. Via eigendecomposition, we broke it down into n matrices. All of them are also n by n. And each of these matrices has a scaling factor, lambda 1, lambda 2, lambda n. And V1 transpose is called a projection matrix. We're going to show with an example, show what that means. All it does is it projects X, which is what we're transforming, onto the eigenvector VI. These eigenvectors are also called principal axes. And the projection of X onto those eigenvectors is called principal components. There's another technique called principal component analysis. It's basically single value decomposition from a different direction. So it's basically the same thing. So we can skip this. I think this is too much. So this is an example. So we have a matrix X shown in red, and we have an eigenvector V shown in blue. And we want to project X onto V. The way it's done is you draw a line perpendicular to V. And obviously V is too short, but you extend the line. At some point, this green line meets it. And that would give you another vector, which is the projection of X onto V. And it's given by V transpose X. So if you go back to this formula, so if you multiply A by X, you have n terms which have V1, V2, V1 transpose X all the way to the nth entry. Okay, so next we multiply that let's do this for the first entry in here. AX equals lambda 1 V1 V1 transpose X. V1 V1 transpose X is a projection, which we already did. Next is we multiply it by lambda 1. And multiplication, as we know, doesn't change the direction. It only changes the magnitude. So if you multiply that blue vector by lambda, you're going to get a purple vector, which is bigger because lambda is greater than 1. If lambda was less than 1, it would become smaller. Okay, so now we learned how to project and scale for one eigenvector. If we repeat this for all the eigenvectors, instead of one purple vector, we're going to get n purple vectors. In the two-dimensional case, we're going to get 2 purple vectors. So I'm projecting X onto V1 and scaling it. I'll get the purple vector on top. I project X on V2, which is in the lower part of the graph, and I scale it, and I get the purple vector V2, purple vector number 2. And if you add these together, you're going to get the yellow vector. So that's what a symmetric matrix does. A symmetric matrix of n by n has n eigenvalues and n eigenvectors. What the transformation does, it projects that input vector X onto those eigenvectors V1 and V2, and then it scales them by lambda 1 and lambda 2, and we get 2 vectors. We add them up, we get the yellow vector, which is the result of the transformation. Another concept that we have to talk about is rank. Rank of a matrix means the number of linearly independent columns in that matrix. So you could have a matrix of size m by n, but if some of the columns are not linearly independent, the rank is lower than n. So basically, I'm going to skip over this. If rank of A is the dimension of AX, so if you multiply transformation A by X, what is the dimension of the result? That's the rank. So this is the summary of symmetric matrix transformation. The symmetric matrix symmetric n by n matrix A transforms a vector by stretching and shrinking it along its eigenvectors. The amount of stretching and shrinking is proportional to the corresponding eigenvalue, and X is projected to each n eigenvector and then scaled by the corresponding eigenvalue. And then we add up these n scaled vectors to create the transformed vectors. So here's an observation. We're adding n vectors together to create the resultant vector. The length of these vectors is important because if you add 2 vectors, one of them is much smaller than the other one, the resultant vector mostly relies on the larger one. So the larger the eigenvalue, the larger the contribution of the scaled vector to the transformed vector. So what this means is that we can approximate A by taking the top k vectors in terms of their magnitude and adding them up. And this will give you a great or very good approximation if the last n minus k eigenvalues are very small or almost 0 or very small, close to 0. So that AK would be an approximation of A. We repeat the exact process that we did up here in this example, only we reconstruct the yellow vector using the top k dimensions based on the eigenvalue. So in this case, if we were to use the top, well, it's 2-dimensional, so we can use 1. Which one of these purple vectors would be using if we're doing an approximation, the top one or the bottom one? It would be the top one because it's a larger vector, and the bottom one can be ignored. So that's the idea of, but you can do this in n dimensions. So if you have, I don't know, 50 dimensions, instead of reconstructing a vector from 50 scaled vectors, maybe we use 10 of them. So singular values, so we discussed what symmetric vectors are and how they could be decomposed. But there's still a problem that not all vectors are symmetric. Some of them are asymmetric. So how are we going to deal with that? That's what singular value decomposition does. So the idea is if you have a A matrix A, which is m by n, not symmetric. If you calculate A transpose A, based on this calculation, it would be an n by n matrix, which is symmetric and squared. So what we do is, if you have a matrix that is not symmetric, we calculate A transpose A, which is symmetric, and we calculate the n eigenvectors eigenvalues for that matrix A transpose A. They give us the direction and the amount of scaling for A transpose A transformation, but they don't tell us anything about direction of stretching and the scale for AX. So what can we do? So if this comes without proof, if we look at AX, the first direction of stretching is the direction of the vector that has the greatest length, and that equals AV1. The second direction of stretching is the direction of the vector that has the greatest length and it's perpendicular to the previous direction. That's equal to AV2. I'm not going to show the proof, but let's just accept it. And same thing, we can go on all the way to the nth dimension. The transformation of the eigenvector for ATA by A gives you the direction of stretching in AX. So let's see what that means. AV1, AV2, AV3, they give you the direction of the stretch. This is vector, the length is not 1. We want to deal with vectors who have a length of 1. So let's calculate the length of AV1. With some replacement, we're going to get that lambda I. So lambda I is AVI to the power of 2. That tells us that all the lambdas are positive, because if it's a squared value, it could be 0 or greater than 0. Second thing is, if we take the square root of that, the square root of lambda is called sigma I, or singular values. So we know what singular values are. Let's look at the singular value decomposition. It's something similar to eigen decomposition. Matrix A can be broken down into 3 matrices, U, sigma, and V transpose. Sigma is a diagonal matrix with R sigma values. If the rank of A is R, it's also padded with zeros at the bottom and at the right. V are the n eigenvectors of A transpose A, and U are m vectors that show the direction of stretching in AX. So you can simplify this multiplication, and we get something very similar to eigen decomposition. So here A is represented by R m by n matrices. Each of them, again, similar to eigen decomposition, have a multiplier, sigma 1, sigma 2, sigma R. And each of them also do a projection, U1, V1 transpose, U2, V2 transpose. So it's a similar concept. If you want to see what the transformation of A does, and A is a non-symmetric matrix, you project AX onto U1, U2, UR, and then you scale it. So similar, the matrix projection scaling that we saw before. So single value decomposition decomposes A into R matrices of size m by n. Sigma I is the scalar, UI is an m-dimensional column vector, VI is an n-dimensional column vector. You multiply them, it's an m by n matrix. So each sigma I, UI, VI transpose is a projection matrix. Projection is you just move one matrix onto one eigenvector. And so the geometric interpretation of SVD is any linear transformation can be decomposed into 3 transformations: rotational reflection, followed by scaling, followed by rotational reflection. So that circle to ellipse transformation, you do a rotation, you scale it, and then you rotate it back, you go from one to the other. That's the whole, that's everything about single value decomposition. you can represent any linear transformation by 3 simple transformations following each other. Reflection or rotation, followed by scaling, followed by reflection and rotation. So let's look at an example. We have a matrix A, which is not, it's square, but it's not symmetric. So we can't use eigendecomposition to find the eigenvectors. So the trick, the workaround was that we calculate A transpose A, which if you see, it is symmetric. And we calculate the eigenvalue and eigenvectors for this A transpose A. So we have a circle on the left-hand side and we have one point X displayed on it. On the right, we have that circle transformed by A transpose A. And as you can see, the eigenvectors and the eigenvalues give you the direction and the amount of stretching. But we're interested in AX. We're not interested in A transpose X. So what we do is we take this X1 matrix, we project it onto V1 and V2. We get these 2 values. Then we go to the ellipse, and we know the maximum direction of stretching is given by AV1, AV2. Those vectors, they don't have a length of 1. So we divide them by their length and we get U1 and U2, which are giving us a direction of stretching and have length of 1. And finally, if you look at the formula, what we have to do is we have to multiply sigma 1 by V1 transpose on U1. So let's go back. So that's what we did. We have 2 yellow vectors. That's U1 multiplied by the sigma 1 and multiplied by the V1 transpose X1, which we calculated here. So we have 2 yellow vectors. They're kind of, there's a blue vector underneath and a black vector on top. It's not very clear, but if you add these 2 yellow vectors, you're going to get the transformation by a non-symmetric matrix. So we can calculate this transformation for a symmetric matrix by eigendecomposition, non-symmetric matrix by singular value decomposition. Both of them are, I gave you a 2x2 example. So similar to eigendecomposition, we can also approximate matrix A by taking into account only the top K values of the top K singular values. Again, the formula is simplified. You only care about the top K singular values, so you can ignore some of the columns in U, you can ignore some of the rows in V on the right and left, and you get an approximation. And this is shown to be the best approximation you can get. You can't beat that, it's the best. And it's best, it's not a subjective thing, it is an objective thing. Given this Frobenius norm, it is the best. No matrix B can do better than AK in terms of being close to A per that formula at the bottom. Okay, so in summary, matrices represent linear transformations. Matrices could be symmetric or non-symmetric. We can, if a matrix is symmetric, we can use eigendecomposition to break it down into 3 operations. If it's non-symmetric, we can use single value decomposition to break it into 3 operations. And single value decomposition says that any matrix transformation can be represented by rotational reflection, followed by scaling, followed by another rotational reflection. Perfect. So what can...
Hey, Kamali, one question I have. This is Vijay. How do you fix that K values? I mean, how to choose that, what number of K values to be taken?
That's exactly what I'm going to show now. That's a great question. Thank you. And I think it will come clear now. Okay. So there are many applications of singular value decomposition. I mean, it could be in multiple presentations themselves. One of them is to select the value of K and do approximate reconstruction of a matrix. And that is used extensively in image analysis. So this is Diego Maradona after winning the World Cup in Mexico. And what I did was I made this image grayscale. It's just easier to work with grayscale images. So we have a matrix. The matrix size is 1836 by 2928. Let's assume this is A, the transformation matrix that we discussed. Every element of this matrix, depending on the representation, it could be a value between 0 to 1. 0 means, I think, black, 1 means white, and anything in between, it's a shade of gray. Or it could be 0 to 255 if it's 1 byte. Okay, so what we can do is we can calculate, this is a non-symmetric matrix because the number of rows and number of columns do not match. So what we can do is we can calculate the singular value decomposition of this matrix. It's going to give us, go back to the formula. So this is the formula. A means equals U sigma V transpose. And then we can do an approximation, which is we take the top K eigenvalues. That gives us AK, which is an approximation of A. Okay. So I'm going to do that for different values of K and see what image we get back. So the best value of K is somewhat subjective to answer that question. Depends on what is acceptable to you. So this is the grayscale image. If I take only the top singular value, this is the image that I get back after it's reconstructed. So it's useless. You don't know what it is. If I take the top 11 singular values, this is the image. I mean, most people can't tell what it is. If you take the top 51 out of over 2,000, this is the image. It's somewhat, I can tell what it is, but I'm a football junkie. Maybe not everyone can tell. This is 101, 151, 251. This is actually pretty good. 551, I think it's clear. And then the improvements are not as much noticeable. 1001, 1501, 2001, 2501, 2921. So what does that mean? Okay, so we converted the image to grayscale. We calculated single value decomposition, and we reconstructed the image using the top K singular values out of 2928. So the original image is like 1836 by 2928 matrix. So it has 5,300,000 and it changed values. Values could be a byte or whatever. We don't care. But if we reconstruct it using the top K, K being 551, then the number of values drops to 2.6 million, which is almost half of the original image. If we go to 251 top singular values, we would have slightly over 1 million values, which is a 77% reduction. So let's put these images next to each other. This is K being 551. The original image is on the left. The reconstructed approximation is on the right, and we have a 51% compression. Okay, so that's pretty sizable. If you have tens of thousands of images that you have to transfer, and you are okay with losing a little bit of quality, you get a huge benefit by compressing, reconstructing these images. This is the case where you're using 251 top singular values. The compression ratio is 71%. That's even better. I think the picture on the right is still pretty good. So other applications of singular value decomposition, in natural language processing and text analysis, there's a technique called latent semantic analysis or indexing, LSA, LSI. It's basically singular value decomposition on documents. So the way documents are represented in text analysis is that you have maybe all the words in columns of a matrix and all the documents in rows of a matrix. Okay, so maybe you have 10,000 documents, so you have 10,000 rows, and all the words are in the columns, and English language has like, I don't know, several 100,000 words. So that's going to be a mighty big matrix, and most of them would have 0 values because not every document has every word. But if you want to find a pattern in there, you can use single value decomposition. For example, you have some documents that are about Asian cuisine, some other documents about Mexican cuisine. You know, if you want to use distance-based methods, you know, really, you know, distance-based methods don't care about the distance between Chinese and a Mexican word is the same as distance between a Chinese or an American word. So it's not really helpful. But if you use some single value decomposition, you can come up with concepts, and these concepts have a weight, which is expressed as singular value. So it could give you insight into the data that you have. Another application is noise reduction. So if you have images that are noisy, you can pick the top K singular values and the noise would be gone. Face recognition, there's a technique called eigenfaces. Again, you can represent an image just as I did with that football image of a face, and you can reconstruct it using the top singular values. And there was a perception that the eyes are the most important feature in terms of distinguishing people. If you run a single value decomposition and try to reconstruct it based on the top K singular values, as I did for that image, you're going to see that the image of the eye shows up first in the reconstructed image if you only pick the top. So it's not it wasn't just an intuition. It's actually, there's math proving that the eyes are the best discriminators, maybe. So there are other applications. I mean, as I said, we could have a separate talk about just single value decomposition applications alone. So getting single value decomposition in Galaxy, there is a Python library called scikit-learn. It's a very nice machine learning library written in Python. And there's an effort by, I think, Galaxy EU and Oregon, I think, to add many of the tools available in scikit-learn to Galaxy. A couple of weeks ago when I checked, there was an issue in Galaxy Europe in terms of using PCA, which is a variant of single value decomposition. So what I did was I added this locally to my local Galaxy instance, the PCA, Principal Component Analysis. So I went through a tutorial on how to add a tool to Galaxy. I wrote this configuration tool. I wrote a Python tool wrapper, and I had it available in my local Galaxy instance. I could pass it to file. It would generate the Principal Component Analysis. The NumPy library also has single value decomposition, as well as the scikit-learn. It's called truncated SVD. It's an optimized SVD. So that can be added to Galaxy as well. Actually, I think if I could do that. Maybe I'll create a pull request for SVD to be added to those list of tools that have already been added from scikit-learn by Galaxy EU and Oregon. So these are the references. The first one is an excellent single value decomposition article. And the second one is also a very good, simple principal component analysis tutorial. I would start with that first because the first one is pretty complex. The second one is simple if you read that. I borrowed some of the transformation matrix examples from Wikipedia articles, and same thing for matrix concepts. So if you have any questions, thank you. And if you have any questions, please let me know. And these are the Belgian defenders trying to figure out Maradona.
So, well, thank you. This was actually an excellent presentation, which makes me feel that I need to ask you to, teach a few lectures for me in my class, let's say. So this has been, there are a lot of areas in biology where it's applied. It's been applied quite a bit in microarray data, because microarray data, it's very much, it's a matrixy kind of a thing. I don't know if you guys know that Kaivan actually teaches machine learning in Penn State, in addition to what he does for Galaxy, and what he does on the Galaxy side is very much removed from machine learning. So that really makes me feel that you're trying to find some application of machine learning in what we do. And so there's sort of a number of I mean, as a project, at least from my lab, we've never quite done this. But I think actually Mike probably does things related to it. But also in Oregon, I mean, Jeremy has been working on that. But here close to home, we have this joint grant with computer science department. And actually, Jeshwant is on this call. He's one of the students of Mahmoud. Mm-hmm. And you know, what we were trying to do there is to find some ways of using GPUs in Galaxy. We, however, didn't really, I mean, we're still sort of looking for a good application scenario. So I would be nice if we, in addition to what you do, Kaivan, already have you with some, but I just don't know at this point, with some kind of a side project related to this. So perhaps we should think of what's sort of what cool stuff we can do, maybe in relation to SARS-CoV-2. I don't know. We really have to think about that. So, any ideas?
I think the application in text analysis that would map closest to like genetic data. Because they have words and documents and they're trying to find concepts, which is kind of vague. But I think maybe I should look into how that's applicable to, you know, genetic data.
So, I mean, the only effort, again, I haven't looked for this that much, but if you Google for lit COVID, that's National Library of Medicine effort to get SARS-CoV-2 publication data under some control, because that's just think about it, it's a remarkable mess. It's been, I mean, people started publishing on coronavirus maybe in January. As of today, we have something like 60,000 publications which are peer-reviewed. Well, there's a lot of shit there, but still they're kind of peer-reviewed. Plus we have probably around 9,000 or 10,000 papers in preprint servers, stuff which is not peer-reviewed. I mean, there are actually some intersection between the two. So yeah, that's a huge. There's no any possibility to claim that when you do some kind of a SARS-CoV-2 research that you read all the papers. It's impossible. So boiling them down to some list of concepts, as you say, might be useful, but we need to check. We're probably not alone who thinks about that. Mm-hmm. Let's so guys, if you have any ideas and you don't want to express them now, we probably should start thinking about this, because we have this wonderful pool of talent on this project, which we, I think are not using in that direction. It's too bad Jeremy is, I know Jeremy is on the call, but it's too early for him, so. Okay. So
okay, I will talk really quick about object stores. I haven't heard any screaming in the last 5 minutes in my background, so I feel like it's due, but wish me luck. I'll try to go really quick here. Can people see my slides?
Yes.
All right, so a couple of years ago, I added this ability to Galaxy to sort of map jobs to particular object stores using, like, presumably this would use like dynamic or job resource parameters. So like this is, I think, BWA mem. At the bottom here, you can send it specific clusters. And the admin has to set all that stuff up. And you can do that with object stores too. I haven't really seen any uptick, but it's there. But then earlier this year, Anton decided that the roadmap needed like temporary disk and scratch space and these things, and we hadn't made a lot of progress in years on that. So last few weeks I've been trying to take this work and seeing if I can make it do that thing.
Just to note, I didn't decide it out of the blue, so. Yeah,
no, it's really needed. Otherwise I wouldn't have done it. So this sort of can do that, right? You can have the users pick, even in their preferences or in their tool parameters, and you can send data to scratch storage. But I think one big problem with it is that all of the object stores in Galaxy currently, as of 2009, share a single quota. And so we have this quota problem where we can pick the object store, but all the quota is the same. So we can't like say like scratch space gets bigger quota, or this really redundant storage. If you select it for published data, it gets less quota. We couldn't do any of that stuff. And so I opened a PR that added a solution to this. Well, there's a PR before this. I wrote these slides really quickly. There's a PR before this that added like better abstractions around quotas. That still needs to be merged, but like testing and abstractions around quota were sort of needed before we could do this. But this PR adds the ability to sort of, for each object store, you can attach a source, a quota, what I'm calling in the PR a quota source label. So like object stores, you can sort of, each one can have its own quota source, or you can like group them together and they can have a quota source, and basically everything that has the same quota source label, has its own quota, and it's distinct from your sort of default quota. So I add this idea of quota source labels so that we could have like smaller quotas for really redundant disk or high. So like if like in Australia, right, they delete everything regularly. So maybe they would want the inverse of what we want in main, where we want scratch space. Maybe they want like, this is the good storage, right? If once your analysis is done and you rerun it, and this is the one you want to save, maybe then you store it to some more permanent storage. The PR also adds the ability to just turn off quota for certain disks. So if you don't need quota on that disk, it's completely scratched, completely temp, you can do that. The admin perspective here is in the object source XML, you can just attach these source tags like here, source S3, or you can sort of disable it altogether with this enable tag. And both of these quota tags are new for the admins in this PR. Once they create the quota source on the object stores, then, so object store is something we track in config files, but quotas are something we track in the database, which sort of makes me angry. But once you've attached quota source labels to object stores, you'll get this new dropdown, and it will only be in the dropdown if you're using this feature. But you can select, when you're making quota operations, you can select which source it applies to. So they can have default sources, users can have more quota on this or less quota on that. All the features that are currently exist for quota sort of work with the quota source labels. The user then, currently when you click that quota meter, you get sent to, this screenshot's a little bit out of date. You get sent to the help page on galaxyproject.org for quota stuff. But now if you enable multiple sources, you'll see the sources sort of broken out, what your quota and usage on each of them is. Yeah, and so that added the ability to sort of really break out these object stores and make them more useful. And unfortunately, well, one limitation of that still was that, yeah, users could select where it goes, but then there wasn't any retrospective data other than their quota usage. So probably users would want to see on a data set where it's being stored and what the disk looks like there. So if it's on temporary scratch disk, they should know that. If it's on really nice disk, they should know that. So I opened another PR that added metadata to the object store itself, to the description. So I added a name and a description field, and the description is markdown, so that you can really like have a really nice description of where the data resides. And so here I put a little example for like what our really nice data on Corel might look like. The PR has another one where it shows like cloud, this is cloud temp disk. We're deleted every 3 weeks. Make sure you don't put anything important there, sort of thing. And it's marked down so you can use images and stuff. Hopefully sort of, we can do markdown in the GUI now. And so hopefully like admins can sort of have a more like, hopefully I like this idea of like, some of the information that we are collecting on these, on our systems are exposed that way. We need a bunch more abstractions. I mean, I think this is a good start. I think admins could really build something cool with this stuff. I think we need to keep going in this direction though. We need to sort of, some ideas I have that I think are important are like tracking the expected level of redundancy or robustness in Galaxy. So like if you publish a page and the object store is marked as like, this is data that gets routinely deleted, you should maybe be warned before you publish a page with that data set. And so like just tracking the level of redundancy or robustness that we would expect in an object store in some way. I had a Boolean, like, is it transient or not? But then I was thinking that's probably not the right way to think about it. We probably want a range of values or tags of values. I don't have any good ideas here. Just it's something I think we need to do and we need to like leverage in the UI. And and then add functionality to transfer. So like right now it's cool that you can see where your data is located, but there's no functionality in the work I've been doing so far to like, okay, this was done on scratch space, but now I want to publish it. And so we need to do something there, I think. I think what I have is useful without that, but I mean, that would be another step. And then, yeah, then sort of a lot of this is like also gearing up towards Vahid's per user object store PR. So I tried to do a bunch of abstractions here that would make that easier, but I think I still think we need more abstractions around that concept of this is that user's data. So like in Galaxy right now, data doesn't belong to a user, right? It's got groups and stuff, and credentials aren't tied to the data set, et cetera. Like the data belongs to Galaxy. I think we all throughout the API and backend, we would treat data differently if we knew it was tied to a user. And so just the UI experience and stuff around that. All right, 2 minutes till 1. Thanks for coming today. I'll stick around for questions, but I mean, I guess the main developer roundtable is over. And thanks for coming, everyone. Any questions about this work now?
Can I go back to cow and foo?
Yes.
Okay, so actually previous slide.
This one. Or
Yes.
this one?
So
This is like if you label it with, this is labeled S3 here. This would be labeled, I mean, count, I don't know why I always use those. But like the label here would show up for the admin here in the dropdown. And then it would show up for the user with the label, and you wouldn't call them food and food.
okay, so the important thing is the next slide. That's admin view.
No, this is admin view.
Okay, well
This
that's
is
what my
user view.
question.
This is, yeah.
Because I was afraid you're actually giving users ability to do this.
I don't. No, that would be a terrible idea.
Yeah, okay.
No, this is an existing admin view. This form already exists. The only thing is that now that apply the rule that you're building, this dropdown will appear, and it will only appear if you've enabled source labels on your object stores.
And then on the user side, you select that per job and per workflow, or?
So yeah, that's up to the admin, right? So we could do it with job resource parameters. We could do it with user preferences. It would be nice to sort of extend maybe the concept of user preferences with history preferences. So like this history goes here. And I think something that would sort of enable that is like some abstractions around like building forms that let you select some of these things. And so that admins can paste together the sort of experience they want that matches their infrastructure. But yeah, it'd still work on the admin side to set this stuff up, right? So it might be nice to have like a flag in the config to say, my dynamic job destinations are not gonna set the object store. So like this is something that purely Galaxy can handle. As the admin, I don't want, you can just sort of select the object store as the user and then take care of all those details. So if you flip that flag, Galaxy's a little bit less flexible, but then Galaxy could sort of say, this workflow, this job, where do you want, like we could take care of those details more automatically. So if you didn't have reason to think your destinations mapped to your object stores in some interesting or exclusive way, then you could imagine just giving that decision to Galaxy and letting it build interfaces and stuff for that. Does that make,
Yeah.
that doesn't make sense.
I mean, especially the per history idea sounds really good.
Yeah, I mean, that is what Anton told me to do, like per history, scratch histories, essentially. I think this is all the backend framework for doing that. I think, yeah, we sort of.
So it's easy. Sorry.
Yeah.
It's easy if you select the object store when you create the history. It can be tricky if you want to change that at a later time, because then you have to move all the data sets, right?
Yeah, just because something's in a history doesn't mean it should be. That should be thought of maybe as like the default destination for that.
So how do you think user can move the dataset from one object store to another object store?
I haven't gotten there yet. I think, a lot of stuff that we want to do sort of depends on the messaging framework. I think one could just do that in a web thread, right? Like one could just like rewrite the dataset object and push it over there, but that's not something that should happen in a web thread. So having some robust backend messaging for random operations like that, I think would be good. I mean, because I could do it in the database, right? I could just like write the data here, change the data set object, and be done. But that is just a matter of where that happens in Galaxy, really. And so maybe
So you don't want to break the reproducibility, right? When doing these moves.
I don't think this, where the data, we don't really track, I don't know that that would break reproducibility. I mean,
Well, I mean, it's normally you have data set n, which is actually a same number, same data set underscore n dot dot somewhere, right? I think that's something you can work around the right abstraction.
I mean, that's, I guess the object store would handle that.
Yeah.
I guess. But I wanted to say that for this sort of task, can we just use the current task messaging that we already have? I mean, there is one mode where, you know, the same process handles the task but returns, so basically an async operation.
yeah, I haven't looked at it. That might be perfect. I haven't played around with it.
I mean, I agree that we should have a nice messaging system, but I think there's also something today that would be usable.
Yeah, I would like to see this work, you get merged and make sure this is the direction we want to go first too. But yeah, I don't know if I want it to be my full-time job to sort of keep working on this particular problem. It's kind of far afield from what I normally do, but maybe it's worth it. Do like the big institutes think they would use this stuff? Is pushing data around different object stores? I mean, I listed it as a problem here, but maybe it's not something that people would want to do. I mean, yeah, I don't know.
I mean, with user object stores, I can see that.
What was that?
With user object stores, I could really see that.
Yeah. Okay.
Yeah, I think there have been various types of requests for ways to manage data at a more granular level before. People ask for different things, but I think what you're building contributes to that.
Okay, well, we're over. Thanks for coming, everyone. I'll post the slides and we can keep the conversation going in the dev channel or Galaxy project or wherever. If I get some reviews on the PRs, that'd be great too. Thanks.
All right. Thank you.
Thanks, John. Thank you. Thanks, Kaivan.
Thank you both.
Thanks, guys. See you all.
Thank you all.